Welcome to the first lecture from chapter number 9. Today we will start studying pseudo-nmos logic. It's a high-speed logic technique and dates back to the early years of microprocessors, when microprocessors were being designed for the first time in the history. It's a very simple technique, simple to understand. The block diagram is given like this. The half part of the logic is nMOS array. It's the same nMOS array as we use in CMOS, but the difference is in the PMOS array. We have a special PMOS array in this technology, which is not an array in fact, but it is a single PMOS transistor. And the second important thing is that this PMOS transistor that replaces the whole PMOS array is always on. This means when the input combination is such that the nMOS array is not on, the output should be logic high, PMOS array should be on. Since PMOS array is always on, when we apply a logic combination which creates an output which is a logic high, it is already available there. So this is the advantage, that we have the output readily available, but the technique has certain advantages. Number one, that output high is readily available, so it saves time for input combinations for which the output is a high. Number two, a second advantage is that we have to have, instead of 2 n transistors that we have in case of CMOS, where n is the number of inputs, if we have n inputs, we need 2 n times transistors to implement a CMOS. In this case, we only require, in pseudo-nMOS case, we only require n plus 1 transistors. So there is a saving in number of transistors, but this saving comes with some disadvantages. The first disadvantage is that since this PMOS array, which consists of only one transistor in case of pseudo-nMOS, the PMOS array is always on. This means VOL, the output logic voltage low, VOL, the actual voltage in volts when the output is low, is greater than 0 volts. Because when we apply input combination for which the output is low, this nMOS array turns on. For input combination for which the output is low, this nMOS array turns on. This PMOS array is already on. This means that both nMOS and PMOS arrays are on. So we cannot have an output voltage that is exactly 0 volts, but somewhat higher than 0 volts. The other disadvantage is its large power dissipation. Power dissipation in case of pseudo-nMOS is larger, because when both arrays are on, a large amount of current flows, causing large amount of power dissipation. Right, after we have studied these basics of pseudo-nMOS, we are ready to draw our first pseudo-nMOS gate. Pseudo-nMOS NOT. A pseudo-nMOS NOT, as suggested by the block diagram, will have a pull-up transistor PMOS, which is always on. Since the gate is connected to ground. This means that VSG, you know, we look for VSG for PMOS transistors, and if it is greater than VTP, the threshold voltage, it is on. And the nMOS array in case of NOT consists only of a single transistor to which we connect the input voltage, and the output is taken from here, right? So when the input is logic 0 for this NOT, means the output should be, this nMOS transistor will be off, because VGS, this is VSGP, this is VGSN, to differentiate that it is for nMOS, and this is the source to gate voltage for PMOS. So this VGSN is 0 because this is 0 minus 0 is less than VTN, therefore it's off. Therefore this transistor is off, and this is always on, providing VDD to the output. That looks fine, but there is a small issue when we have input is equal to VDD, logic 1. This transistor turns on. This transistor is already on, it's always on. This means there is a current ID P flowing, and there will be a current ID N flowing. So both transistors will be conducting, and there will be a current flowing through both, and of course this output voltage VOL, Vout, which is VOL in this case because the input is logic 1, output is logic low, should be logic low, it is VOL, and VOL cannot be 0. Why? Because VOL is the voltage drop across this transistor, right? To compute as the last item for this lecture, let's compute the value of VOL. We know that they are connected in series, so the drain current for PMOS is the same as the drain current for nMOS, but this nMOS is in its linear region, whereas this PMOS is goes into saturation region. So the two transistors are in two different regions, right? We know that we have already studied the characteristics of VDS versus ID in earlier courses. We see a linear region and a saturation region. So one of the two transistors, because the current flowing through this and this is the same, but that will take this, because this gate to source voltage, drain to source voltage is smaller in this case. Therefore this transistor, the nMOS transistor, is in its linear region, whereas this PMOS transistor is in saturation region. So for drain currents, we have two different formulas for drain currents when the transistors are in saturation or in linear regions. Since this transistor nMOS is in its linear region, we have a formula to compute its ID, which is 2 times VDD minus VTN. This is given in my notes as well as in the book. VOL minus VOL squared, and this is equal to IDP, which is beta P by 2. We have studied this formula in chapter number 7. VDD minus VDP squared, right? This formula was studied in EDC course. This formula we studied in chapter number 7, the last chapter, right? So now we have to compute the value of VOL. We have VOL here and a VOL here, and here it is VOL squared. So it seems we will finish up with the quadratic equation, and we'll solve using quadratic formula. Right, so let's first cancel this 2 with this 2, and then divide this beta n over here. It becomes beta p over beta n, and this becomes 2 VDD minus VOL, 2 VDD VOL, 2 VDD VOL minus 2 VTN VOL minus VOL squared. So if we take everything on the right hand side, this becomes VOL squared, taken on the other side becomes positive, this becomes negative, this becomes positive, minus 2 VDD minus VTN VOL, and this remains positive because we are going on that side, plus beta p on its side, beta p VDD minus VTP squared. So everything else is now gone, and we are left only with this quadratic formula. The solution is using this quadratic equation. We are left with this quadratic equation, and the solution is by using quadratic formula. That is VOL is this, the coefficient here A is 1, the coefficient B here is minus 2 VDD minus VTN, and this whole is C. So the formula is minus B, 2 VDD minus VTN plus minus B squared. B squared. This is 4 VDD minus VTN squared. B squared minus 4, A is a 1, C, beta P over beta N, VDD minus VTP squared, and this whole is a square root divided by 2A. 2A is a 1. So if we take this 4 common out of these 2 and take it out of the square root, this becomes 2, and this 2 taking 2 common, so everything cancels with this denominator and even this 4. Right, so we are left with this expression. It's a very interesting expression because it has 2 answers, plus and minus. If we add these 2, the answer is very large. So it's logical. You can try it at home. You can try it at home for different values of VDD, VTN, beta P and beta N chosen from chapter number 8. And it's a homework for students to try both. Homework to try using plus and minus signs, and you will reach to a conclusion finally that the realistic answer, the correct answer is obtained by keeping this minus and deleting this plus. So only one option generates the correct answer, and that is this is minus sign, but you can try at home with plus and minus signs. So we'll keep on studying high-speed logic circuits in chapter number 9 in our upcoming lectures. Thank you.